So you're deep into some Python code, working with data, and you've got lists. They work, right? So why does everyone keep talking about NumPy? What's the big deal? Well, today, we're going to pull back the curtain and see exactly why NumPy is so critical for any kind of serious computing in Python. Let's just jump right in and look at this. On the left, you've got C code. It's a lot. You have to spell out every single little thing for the computer. And then on the right, that's Python. It's clean, it's intuitive, it almost reads like plain English. It's no wonder so many of us fell in love with this language. But here's the twist. That beautiful simplicity, that incredible flexibility, it's a double-edged sword. It actually comes with a hidden cost, something happening deep down in your computer's memory. So how on earth can Python's best feature also be its biggest weakness? To figure that out, we first have to talk about what makes Python so darn friendly in the first place. This thing called dynamic typing. It's pretty much the magic behind the curtain. Check this out. You can say x equals 4. Cool. Then, on the very next line, you can say x equals the word 4. You just swapped a number for a piece of text. In a language like C, the computer would just freak out. But Python, it just rolls with it. That is dynamic typing, and it's why Python is so incredibly easy to just pick up and use. But, like I said, that convenience isn't magic. It's not free. There is a ton of work happening behind the scenes. And to really get the cost, we have to zoom in and ask a really basic question. When you create an integer in Python, what are you actually creating? See, the truth is, a Python integer isn't just a number, it's so much more. Under the hood, Python is built on C, and every single variable you make is actually this big, complex C structure called a Python object. It's not just holding your value, it's carrying around a whole bunch of extra information about itself. And this slide just lays it all out. Look at all this baggage that every single integer has to carry around. You've got a reference count for memory management, a type code screaming, "Hey, I'm an integer," a size field, and then way down at the bottom, buried under all that overhead, you finally find the actual number. Think about that. All that extra information for every single number. Okay, so if that's the overhead for just one number, imagine what happens when you try to put a bunch of them together in a good old Python list. This is where things start to get, let's just say, messy. Now, all that extra baggage is what lets Python lists do this crazy stuff. You can just throw anything you want in there. A boolean, a string, a float, an integer, it doesn't care. It is the ultimate anything-goes container. So you have to wonder, right? How does a computer's memory, which is all about neat, orderly blocks, actually handle a collection this chaotic? Here's a great way to picture it. Don't think of a Python list as a neat shelf with items all lined up. Instead, think of it like a binder. And inside that binder, you've just got a bunch of tabs. And each tab just tells you where to find the real file folder, which could be stored anywhere. So here's the crazy part. The list itself, it's not even holding your data. It's just a list of pointers, like addresses. Each of those pointers then sends the computer off to some other random spot in memory to find the full Python object, with all its baggage, the type info, the reference count, the whole shebang. It's incredibly indirect, and, well, pretty inefficient when you think about it. And this is the exact problem that NumPy was invented to solve. It comes along and says, let's just not do any of that. It throws out all that indirection for pure, raw, efficient power. So if the Python list is that messy binder, a NumPy array is like a perfectly pristine spreadsheet. Every single cell is in a nice, neat row, and they all hold the exact same kind of information. No surprises. And here it is, the big reveal. This is the whole game. A NumPy array gets rid of all those layers of pointers. It's just one pointer that points to one big, solid, continuous block of data in memory. And since every single item has to be the same type, all integers or all floats, it doesn't need to store all that extra type info for every single element. It's just the raw numbers packed tightly together. That right there is why NumPy is so much faster and more memory efficient. All right, that was a lot of theory, but the best part about NumPy is that all this underlying power is still super easy to use. So let's stop talking about it and actually see how simple it is to build one of these super efficient arrays. Okay, let's say you need an array with 10 zeros in it. Simple, np.zeros, done. And bam, there you go, a clean, uniform, memory-perfect array, all ready for you to work with. Need to work in more than one dimension? No problem. How about a 3x5 grid of floating point numbers, all set to 1? Again, one simple, easy-to-read command. And just like that, you've got a two-dimensional array. This is the kind of data structure that's the backbone of everything from image processing to training massive AI models. One more, just to drive it home. You know Python's range function, right? Well, NumPy has its own souped-up version called Arrange. Here we're just saying, hey, give me all the even numbers from 0 up to 20. And there's your sequence. It's pretty clear, right? Creating these powerful arrays is just as easy as making a Python list, but now you know about all the incredible performance benefits hiding just under the surface. So, we've established that NumPy arrays are way more efficient with memory. That's a huge win, but honestly, that's just the tip of the iceberg. The real magic, the thing that changes everything, is what happens when you start doing math on these perfectly structured arrays. What if you could perform an operation on that entire block of data all at once? Well, that is the secret to the speed that powers all of modern data science.